So as you all know, your exam, your last hourly exam is on Friday, and it covers classes 23 to Monday, which was class 25, excuse me, 35. That would be good, huh? Yeah, that would be wicked good. 35. Remember, you're allowed 1 page of notes, both sides. It's a non-calculator active exam, so that should automatically knock out some types of problems you couldn't do without a calculator. So think about that a little bit. So when I said that in my last class, someone said, "You mean I can't add?" Remember, this test will be over at 11:50 or noontime. You have 10 to 10:40 with nothing scheduled. Get here early. That gives you can relax. You have 2 full hours. Bring in some, drinks and refreshments, whatever you want. Okay, but get here early, right? So you don't have to feel rushed. Project 5. Those of you who have your schedule out, William, know when Project 5 is due, and when is that? The 9th. So Project 5 is due May 9th. When is May 9th? That can't be May 9th. It's a Friday. Okay, so it's a week from Friday. We can actually make that May 12th if you want. It's on Moodle. I've put it on Moodle, so just download it. It's a review for the final, so that will help you study. And section 4.4 is what we're going to cover today. This will not be on the test. The review is right back there, that yellow sheet I gave you, okay? The study guide is yellow. I don't have that on Moodle because I had enough copies for all of you to get it. And I changed it so the old solutions have problems from the last test. I just changed the order with the snow days and stuff. I could put up the old solutions, which would cover some of this, and if I have time, I will try to get in here and do a new video for this study guide and put it up. But otherwise, just call me, email me, whatever. Just don't call me at 11:30. So I go to bed usually by 11. All right. Yeah, in the morning. Yeah, I go to bed in 15 minutes right during the middle of class. You never noticed I was sound asleep? No? All right. You do? You go after this class? All right, so today we're going to cover exponential equations and logarithmic equations. And what you need to keep in mind is that how you have learned to solve equations from your beginning algebra class to now to today is not doing anything any different. You solve a linear equation, for example, by doing inverse operations to both sides of your equation. You add and subtract both sides of your equations, you multiply and divide. So you look at what's been done to x and you undo it. The same is true with these types of equations, because exponential and log functions are inverses of each other. They undo each other. So if you start off with an exponential equation, to undo exponential, you apply logs to both sides. Could someone get that door for me, please? Thanks, CJ. If you start off with a log function, you create an exponential equation to solve it. However, once in a while with exponential equations, there's a really quick and easy way to solve them. And we've sort of been doing it all along, but I haven't given you a formal, this is what you're doing type of thing. So let's take a look at number 1 here. First of all, an exponential equation is an equation containing a variable in the exponent. So here's your first look at an exponential equation. Your variable x is upstairs in the exponent. It's your superscript. That makes it exponential. Some exponential equations can be solved by writing each side of the equation as a power of the same base. Another way, and then you equate your exponents. If you can get the same base to make them equal, you just say, I set my 2 exponents equal. And sometimes this is called relating the bases, and that's usually how I refer to it, because saying all this is a lot of language. So can we relate these bases? So the question that you really want to ask yourself is, the left-hand side is already written as a base to an exponent. And the question is, can we write the number 27, which is on the right-hand side, can we make 27 as 3, because that's our base, 3 to a power? So can I represent the right-hand side, can I represent 27 as 3 to some power? What's our answer? Yes. And what would that power be? 3, right, Dan? Okay. So I can rewrite 27 as 3 cubed. So to solve this equation, since my bases are the same, 2x plus 1 has to equal 3. So all you do is you equate your two exponents, and you solve for x. So here, 2x equals 2, x equals 1. And you're a happy camper, you're all done. You can always check. Always go back to your original equation and substitute your solution in for x and see if it's true. So 3 to the 2 plus 1 is supposed to equal 27. This is what we're checking. 3 cubed equals 27. You're a happy camper. There you go. Okay. So if you can make, sometimes you might have at first when you look at it, you might know you might have two different bases, but you might be able to write both of them in terms of the same base. Like if you had 9 on one side, like suppose I had 9 to the 2x plus 1 equals 27. You can change 9 to 3 squared and 27 to 3 cubed. So we just involve one more step. So for example, if this looked like this, okay, you might say, I can't write 27 as 9 to a power easily. And so you say, no way I can use this method. But remember, 9 can be written as 3 squared. So you could make both of these the same base by writing 9 as 3 squared like this, and then 27 as 3 cubed. It's supposed to be blue. 3 cubed. The only thing here is you would have to do one more step here, because notice you want to write this as 3 to some power. So in order to write it as 3 to some power versus 9 to some power, you now have to use your exponent rule where you have a power to a power, so you multiply your power. So this would be 3 to the 4x plus 2 equals 3 cubed. And now you can set your two exponents equal and get your answer. So it's going to be a fraction, and it's, okay, 4x plus 2 equals 3, 4x equals 1, x is a quarter. So check that out. Throw a quarter in up here, you get 2 times 1 quarter plus 1. 2 times a quarter is 2. 2 plus 1 is 3. Uh-oh. What's going on here? What did I do? Oh, 3/4. No, what did I do? Four x plus 2 equals 3. Yeah. Huh? Never mind? Why, you were telling me what to do. If I put a quarter in here, what did I do? Oh, 1/2 plus 1. Oh, okay. Thank you. I just did my math wrong. Oh, and I'm a math teacher. So I go back and check, and I get, oh, I called it 2, not a half. 2 times a quarter is a half. A half plus 1. This is a review of fractional exponents, which was way back in chapter P. A half and 1 is 3 halves, because 1 is 2 halves. So this is 9 to 3 halves equals 27. So 9 to the 3 halves says take the square root of 9, I get 3. 3 cubed is 27. I'm a happy camper. So if you happen to start off with something that doesn't look like it's the same base, or that you, like here where you can just turn 27 into 3 cubed, first check to see if you can make the same base on both sides, because sometimes you just have that little extra step. Okay. All right, so let's take a look at our next one. So here I've formally wrote out both methods. Solve by relating the bases if possible, and if not, we're just going to go right back to what we're familiar with, which is undoing using logarithms on both sides. All right, so the first question is, you see 2 to the x equals 32, and if you're familiar with the game 2048, you know 32 appears in 2048, and therefore you know it is a power of 2. So can we rewrite the right-hand side of the equation as a power 2? Absolutely. How do I write 32 as 2 to some power? 2 to the power 5. So you can quickly solve this equation, like almost like in your sleep. 2 to the x equals 2 to the 5th, so I set my two exponents equal. X has got to be 5. Done. That's how quick and easy you can do some of these exponential equations. Well, unfortunately, they all can't be rewritten that way. Well, actually, I just thought of this in between classes. I don't know if I'm going to like really scare you if I do this. Will I scare you? I hope not. Remember that, because I thought about, well, I'll wait and do it this way and then I'll show you. All right. Solve by undoing with logarithms. Okay, so we know solving an equation is performing inverse operations on each side. I undo an exponential equation by taking the log of both sides. So you say, well, which log? Well, I'd like to be able to use my calculator to get some approximations sometimes of my answers. So I'm going to use either log base 10, your common log, or a natural log. Okay, now most of the time, if your base is other than 10, which in this case your base is 2, it's sort of the standard, even though it doesn't matter. You could do it either way. You could take the common log of both sides or the natural log. And we just use the natural log unless the base is 10. So I'm just going to take the natural log of both sides. So I'm going to change my color here and say the natural log of 2 to the x is equal to the natural log of 32. Okay. Now, I want you to start to train your eyes so you don't hyperventilate every time you see these ln's or logs, that the natural log of 32 is just a number. It's a constant. Just like if you saw something like 2x equals 10. 10 is a constant, 2 is a constant. You would solve for x. This is just a constant. So for now, I'm going to probably repeat myself several times, and I'm just going to put this in parentheses and say, remember. Deep breath. Just a little old constant. That's all it is, little old constant. So if you want, just visualize a number sitting there like 10 or 5 or 20, whatever you want. Okay. We still have a problem though. Our exponent is what we're trying to solve for, and it's a superscript. It's still the exponent. It's still the power. We need to bring it down in front. How are we going to do that? What'd you say, William? X ln 2, that's our log property, right? Our power rule for our log property says I can take this power and scoot it right down in front and multiply my two powers. X is a power, ln 2, natural log of 2 is a power. So I'm just going to multiply those two, and that equals the natural log of 32. Again, that is just a constant, and that is just a constant. So in your mind, when you see something like this, you could think of a very simple thing like this, 3x equals 6. Right? If you had an equation like this, how would you solve both sides? You would divide both sides by 3 because 3 is the coefficient of x. 3 is the constant factor of x. 3 is multiplying x. So to undo it, you divide. Same thing here. What's the coefficient of x here? The coefficient of x, the constant factor, is natural log of 2. So In your mind, you can think this and say, what would I do to both sides? And that still applies. You divide both sides by the natural log of 2. And now you have the exact answer for your equation. It's the natural log of 32 divided by the natural log of 2. All right, so yes, and I'll show you that in a minute. So what do we know this answer has to equal? What does natural log of 32 divided by the natural log of 2 have to equal? 5, because we just solved it over here the other way, right? And if you throw that in your calculator, you will get a more simple answer. Natural log of 32 divided by the natural log of 2 is 5, okay? So if I ask you to simplify it or estimate it, in this case, often you estimate it with, like, it's a decimal answer and you would estimate it, but this you can say is exactly the same as the number 5. So there's my exact solution. I don't even have to estimate it because my answer is a rational number. All right, so Chris just said, would it matter if I took the common log of both sides? Well, let's see. If I took the common log of both sides, the only difference is down here, instead of saying natural log of 32 divided by natural log of 5, it would say log of 32 divided by log of 5. So let's see. Log of 2, thank you. All right, so let's try that. You know, it's kind of weird that, geez, why is it that they both equal? You know, it's like, it seems like it shouldn't be. Log of 32 divided by log of 2, 5. Okay, so it doesn't matter whether you take the common log or the natural log. Someone might say, why don't I take log base 2 of both sides? You could. You could take log base 2 of both sides. It's just a little more work to get your answer. So let's look at it. I didn't do this in my first class, but let me show you. Yep. You don't. All I'm saying is that some people just kind of get into a rhythm. And unless this number is 10, we're using log 10 is going to immediately create a 1, because log base 10 of 10 is 1. So unless your base is 10, we just tend to use natural log. But it does, your tendency could be to use common log if you want. It doesn't matter. Okay. So let me just quickly show you what would happen if you said, well, geez, you know, Linda, I got 2. What was my problem? 2 to the what? 2 to the x equals 32, right? Is that what it was? Okay. So you might say, if I'm supposed to use, this is an exponential equation base 2, its inverse will be log base 2. So why don't you use log base 2 on both sides? The only reason I don't is because I don't have log base 2 in my calculator, but I want to show you I could. So I'm going to take log base 2 of both sides. Log base 2 of 2 to the x equals log base 2 of 32. As long as you have a calculator, you're really fine. And, you know, so in some ways, this makes a little more sense to us because we're undoing an exponential of base 2, a 2 to the x, with log 2, its inverse. So what's the answer going to be here? Log base 2 of 2 to the x. What happens? What's my answer? X. Because I'm saying 2 to what power gives me 2 to the x? When my base here and my base here are the same, what I've done is I've composed my exponential function. I've put it in my log function. I always come back when I compose inverse functions to my original input, which is x. So this is x on that side. And what do I get on this side? Log 2 of 32. So I have to use my change of base formula, right? In order to put this into my calculator. My change of base formula says either use log or natural log. I take the natural log of 32 and I divide it by the natural log of 2. Voila, exactly the same answer that I got back here. Okay, so as you can see, it doesn't really matter which log we use on both sides. The most important thing is that we use the same log, the base of the same log on both sides. Okay, so how about this one? Can I relate this answer? Can I make 25 equal to e to some power? Not easily. Not easily, but you can. Not easily, because it uses that log property you never want to see again. But what does the log property look like? B to the log base b of x, right? If you have b here and b here, this is your log function composed with your exponential function. You come back to x. So I could, this is the thing I didn't show in my first class because I just thought about it in between. I could write 25 as e to the natural log of 25. Because look, this has the same base e, so my answer is 25. So I could write it like this. And I've got my answer. My bases are the same. X equals natural log of 25. But I doubt you're going to think of that off the top of your head. And I wouldn't blame you because you haven't really worked with these log properties a whole heck of a lot. But you could relate the bases. It's just it's not as easy as saying 32 is 2 to the 5th. You have to use your inverse properties here to do this. So this is, maybe something for a later time in your life when, you're retired and you want to come back and visit logarithms or something. All right. So you'd look at that and you say, I can't easily relate the bases. I'm going to undo it. And in this case, because your base is e, you would naturally use natural log of both sides. Natural log of e to the x equals natural log of 25. The natural log of e to the x. Well, suppose you didn't recognize that this is automatically x, because my bases are the same, e and e, so I just lift off my exponent. Suppose you used your log property. You say, I'm going to bring the x down in front. X times the natural log of e equals the natural log of 25. Well, what's the natural log of e? E to what power gives you e? 1. So this is just a big fat 1. So that's why this answer, you can go right from here to x equals natural log of 25, or if you take the extra step of bringing the exponent down in front, natural log of e is always going to give you 1, just like the common log of 10 will always give you 1. The log base 2 of 2 will always give you 1. So this is x equals the natural log of 25. Same answer we got back here. Yep, Chris? It doesn't matter. It doesn't matter, yep. Yes. If I say, because this is the exact solution, because look, if you go back and check it, Gina, it's e to the natural log of 25. There's your composition of your inverse functions. That cancels and you get 25 equals 25. You come right back to where you started. So that's what I was showing you over here, but you probably wouldn't think of that on your own. All right. Any other questions? If I ask you to round your answer to a couple of decimal places, like 2 decimal places, then you would take this answer and you'd throw it in your calculator and you'd round it to 2 decimal places, to your hundredths place, okay? But most of the time I'm going to ask you for the exact answer. I don't know what my math lab does. It might ask you to round. So do you need me to show you how to round that, or are you okay with that? Okay. All right, so let's take a look at these 3 equations. I'm going to put some lines straight down the middle here so I give myself some room here. All right, so there's a little more going on here. Notice, I don't know if you can notice, but my expression, my exponents, each of the exponents here have the variable I'm trying to solve for. So I made that bold. It is bold on my paper. It's not on yours, but I bolded it. Can you see that it's bold? A little bolder than the rest of it? A little bit. All right, it's probably just because they're small. All right, I'll make them a different color. Okay, so you can do this on your own. You can always make, I don't want to mess with that. It's going to look a little crazy. All right, so So here we have an equation, and as always, you want to isolate your variable. Just like you always want to get x or t or whatever you're solving for on one side of your equation and your constant on the other. That's always your goal. So in order to get 1 minus x, that's your exponent, from being up in the air as a superscript, you have to use your log property, your power rule for your logs. However, there's one little thing you need to know. Anytime you have an exponent that is more than one term, put it in parentheses. So this next one, b, is just one term. This is a binomial, that's a binomial. So anytime you have an exponent that's a binomial or 2 terms, 3 terms, whatever, put it in parentheses. It's going to be important, especially when we get to C. All right, so let's take a look at this. What would I do to undo the exponential equation with base 2? What would I do to undo it? I could take the natural log of both sides. I could take common log of both sides. I could take log 2 of both sides, but I'm going to use natural log. Natural log of 2 to the 1 minus x equals natural log of 3. Just take the log of both sides. As long as the log has the same base, you're kosher, okay? Now, I use my power rule for my logs, and that power rule is going to take that power and bring it right down in front of the natural log of 2. There we go. And now I have a coefficient. This would be just like the problem, some number times 1 minus x equals another number over here. So I'm going to divide both sides by the natural log of 2 because that's the coefficient. And I get 1 minus x equals the natural log of 3 over the natural log of 2. Now remember, this is just one ugly constant. That's all it is. It's just a constant. Okay. So how would I solve this equation for x? I'm going to add x to both sides. I get 1 equals that ugly constant, natural log of 3 divided by natural log of 2 plus x. Now to get x all by itself, I subtract away the constant from both sides of my equation. Natural log of 3 divided by natural log of 2. I'm going to subtract it from both sides. So my left side becomes 1. Take away that constant, natural log of 3 over natural log of 2 equals x. That's my exact solution. I'm done. Okay. If I ask you to round this off, all you do is you pull out your little handy dandy calculator. Handy dandy calculator, where are you? It's hiding, so I'll close it and open it up again. Okay, I've got all the tricks now. So let's estimate this. 1, take away parentheses, the natural log of 3 divided by the natural log of 2 is negative 0.584927. So let's say we say x is approximately negative 0.58. So that would be your estimated solution. All right. So any questions on that? Any questions on the algebra here or the ideas used? Anything? All right, let's take a look at the next one. What does the next one look like? The next one, just to sort of give you like some basis for looking at this, the next one could look like this. If I gave you an equation that looked like that, what would you do first to solve for x? If I gave you this equation right here, 100 take away 100x equals 10, what would you do to solve for x? You'd minus 100 from both sides because your goal is to isolate the term with your unknown in it, right? So it's no different when we have exponential equations. Your 0.03t is what we want to solve for t. We got to isolate that. So let's get rid of anything that's hanging on to it by adding and subtracting, or anything that's multiplying or dividing it. So the first thing I'm going to do, just like I would do here, is I would subtract 100 So this is just a little fantasy right here. Here's my fantasy that it's 100 minus 100x equals 10. That's my fantasy. I say I'd subtract 100 from both sides. Okay. So I get negative 100 e, and I'm going to put my 0.03t in a different color so you can see it, equals negative 90. Okay, so if I were using my little fantasy here, my little fantasy would have looked like this. 100 minus 100x equals 10, right? I would have subtracted 100 from both sides, and I would have gotten negative 100x equals negative 90. So if I just had a baby old linear equation, that's what it would look like. What would be my next step on that equation? What would I do? Divide both sides by negative 100, because that's the coefficient. I'm going to do the same thing here. I'm going to divide both sides of this equation by negative 100. And what I'm left with on the left side is e to the 0.03t. And what I have left on the right side is 9/10. Now I'm golden, because now I have an exponential equation with my exponent e to the 0.03t. My exponential expression on the left side is isolated. By that, it means it just has a 1 in front of it. And I have a constant on my right side. So how do I undo an exponential expression that has base e? What would I do to both sides? Natural log, right? I want to do its inverse. The inverse of e to the x is natural log of x. So I take the natural log of both sides. I have a colorful equation here. 0.03t equals natural log of 9/10. I use my log properties. As I told you the other day when we did this on Monday, you're going to use this property over and over again. I bring down my exponent, 0.03t, and it multiplies the natural log of e. That equals the natural log of 9/10. But what is the natural log of e? 1. So that goes away, and I'd simply get 0.03t equals the natural log of 9/10. To solve for t, now it looks like you're used to seeing it. I divide both sides by 0.03. So t equals the natural log of 9/10. I'm just going to write that as a decimal, divided by the divided by 0.03. So let's see what that is in our calculator. Natural log of 9/10. Come on, is it still hiding on me? I guess it is. Close. Open it up. Maybe you can get there faster than me. Natural log of 9/10, natural log of 0.9 divided by 0.03 is negative 0.351, blah, blah, blah. So it's approximately negative 3.51. Okay, so here's a little question for you. If I wanted to check my answer, what would I do? I'll check it wherever you tell me to check it. How are you going to check your answer here? What do I plug back in? Natural log of 0.9 divided by 0.03. If I put that in for t, notice your 0.03s are going to cancel, right? Your 0.03s will cancel. You'll get exactly the answer. You'll get exactly 10. What happens if I put this estimate in, though? Let's suppose you wanted to check the estimate, negative 3.51. What do you expect the answer is going to be? Will it come out to be 10? But pretty close, right? So let's do that. Just so you can see, I don't want you flipping out if you don't get exactly the right answer. Just remember, you're using an estimate. So it's 100, take away 100, oops, take away 100 times e, second natural log, because they're inverses of each other. And what is it? 0.03 times negative 3.51. Negative 3.51. 9.99. That's pretty close to 10. You see, because it's estimated. If you put this in, natural log of 0.9 divided by 0.03. So let's go up here. Let's get my answer back again. Second answer. Oh, that's just going to, yeah, I wanted second entry twice, right? Isn't it second entry? Second entry? Sorry. I could have stored it. Let's just go back. I thought there was a quick way of just inserting, which I think there is. I just forgot what it is. So let's put in the exact answer now. 0.03 times, parentheses, the natural log of 0.9 divided by 0.03. The 0.03s are going to cancel out. Voila, 10. Okay, so you can always check your answer. All right, so I want to show you that you could have done that manually. Yeah, right, Linda, you could. 100 times 100 e to the 0.03. I have faith in all of you. Natural log of 0.9 over 0.03 is supposed to equal 10. You could do this. Your 0.03s cancel. 100 minus 100 e to the natural log of 0.9. Guess what? This is your inverse property right here. This base is e, this base is e. That just cancels and you get 0.9. 100 minus 100 times 9/10 is 100 minus 90, which is 10. You could do it by hand. Okay. All right. Last one. So put your heads down for a minute, take a breath, close your eyes, do whatever you need to do to relax. Relax. This last one takes a while. All right. First of all, you put your, as I mentioned, you put your exponents in parentheses. You're going to have a lot of ln's, ln's, ln's all over the place. Okay? So don't lose, the forest through the trees here. Just take your time. At any point, if I do something you don't understand, please ask. If I go too fast, say, slow down, Linda. All right? So what am I going to do to both sides to bring the exponents down? What do I need to do to both sides? Natural log. All right, the famous answer of the hour. Natural log of 3 to the 2x minus 1 equals the natural log of 7 to the x plus 1. All right. Now I use my power rule for logarithms, and I bring down my exponent on both sides. That 2x minus 1 is going to come down out front here, and it's going to simply multiply the natural log of 3. And on my right side, the x plus 1 is going to come down in front and multiply the natural log of 7. Now, you have to solve this equation for x. So let's have another little fantasy equation going. Here's my fantasy equation down here. 3 times 2x minus 1 equals 7 times x plus 1. Okay, do you see how I kind of made it look a little bit like that? Instead of natural log of 3, I just called it 3, because natural log of 3 is just a number. Natural log of 7 is just a number. So if you had an equation like this, your fantasy equation, how would you solve it? What would you do? You would distribute, right? You would take 3 times 2x and 3 times minus 1. So I'm just going to run this fantasy equation along with us, 7x plus 7. So now, what is 3 up here? It's this natural log of 3. That was our little fantasy. So this is 2x times the natural log of 3 I'm just distributing it. And minus 1 times the natural log of 3 is the natural log of 3. So I just distributed this. That's all I did. You help me. I'm going to be the writer. You tell me what the right side's going to look like now. Okay, distribute the natural log of 7. I'll be the writer. X, excuse me, X times the natural log of 7. Okay, Amy's turned off. Plus natural log of 7. Okay. All right. Now, let's go back to our fantasy equation. If you had this fantasy equation, what would you do next if you had this fantasy equation? You add 3 to both sides, right? That's what you would do next. And you'd have 6x equals 7x plus 10. So basically, you want to get your constants on one side of the equation and your variable with x in it, your variable terms on the other. So let's go up here. I want to move this constant over to the other side, just like I did. So I add it to both sides. There we go. So what do I have on the left side? I still have this thing called 2x times the natural log of 3. This goes to 0. Equals x times the natural log of 7 plus natural log of 7 plus natural log of 3. Notice how I'm using color here to accentuate certain things. Black, well, except for the 2. The black is keeping your attention on where your variable is. And all the natural log stuff's in red. Those are just constants. In fact, I could make 2 red also. Those are just constants. That's all they are. They look really fancy and complicated, but they're just constants. Okay, what would you do now in your fantasy equation? Yeah, how are you going to do that? What are you going to do? Subtract 7x from both sides. Okay, and I'm going to do a little intermediate step that our head always does automatically. Like right now, we would call this negative 1x on this side, but because our head is already, but this is really what it looks like. Well, I'm going to take those print. That's really what it looks like, just so you can see the analogous situation up here. So I'm going to subtract this from both sides. They both have the variable x in them. Okay, so what do I have on the left side? I have 2 times x times natural log of 3. Keep that in red. Take away x times the natural log of 7. And that all equals what? Natural log of 7 on the other side plus natural log of 3. Yeah, it looks really complicated, but again, they're all just a bunch of constants. So what would I do here? What would I do here? You would factor out an x. Now, you say, wait a minute. In my fantasy equation, I never factor out an x. Yes, you do. But you were never told that's what you were doing, because what you were told to do is say, subtract your coefficients, right? You just say 6 take away 7, and then you put an x after it. Well, write that out and look what it looks like. 6 take away 7 times x. You have factored x out of here. X times 6, x times negative 7. This is always a step that's skipped in introductory algebra. I think it would be really important to always see that. Really what you're doing is you're factoring out your common factor x, and you're subtracting the exponents. So up here, we've got to kind of erase our fantasy equation here so we can finish. So look at that expression on your left side. They both have x's, and what you want to do is you want to subtract your coefficients. Here's your coefficient, 2 times the natural log of 3, take away the natural log of 7. Well, again, that sounds a little rough to do, but really what you're doing is you're pulling the x out, you're factoring it. If you pull your x out, what do you have left inside? When you pull the x out of this, you have 2 times the natural log of 3. 2 times the natural log of 3. And when you pull the x out of here, you have natural log of 7. Now, folks, all that is just like this, negative 1 times x. That's all it is. It's just a number multiplying x. This is just a number multiplying x. That's all it is. So how do you get rid of that number if it's multiplying x? How do you undo multiplication? Divide both sides. And you're done. Woo! X equals the natural log of 7 plus the natural log of 3. You can put it in parentheses if you want. All over 2 natural log of 3 minus natural log of 7. And you're done. That's your exact answer. They're all constants. You can throw them in your calculator and you can get an approximation. Are you going to be able to do that on your own without looking at your book or looking at some examples the very first time? Maybe. Maybe not. But, yowza, if you run a fantasy equation right alongside of it, make this into a fantasy equation, I think you can do it because the steps are exactly the same as in your fantasy. I know you always have fantasy about solving log equations, right? Exponential equations. All right. So let's take a look, go back to our rabbit problem. Remember our rabbit problem, the equation that modeled our rabbit problem was 1,000 times 2 to the t, because our rabbit population doubled every single year. And when t was equal to 0, anytime you have t equal to 0, that tells you your initial population, because 2 to the 0 is 1. So we know we started out with 1,000 rabbits, and every single year, so when t is 1, we had 2,000, t is 2, we had 4,000, it just doubles. We have never been able to answer, in fact, I had a question like this on our lecture, how many years will it take? How long is it going to take? So let's highlight that. How many years will it take for the rabbit population to reach 50,000? We've never been able to solve algebraically for that. We could use our calculators. We could always use our calculators to solve for this. And how would we do that? We'd probably put this into y1, this into y2, and we'd see where they intersect. So we could use a graphing calculator. But we now have the ability to do this with algebra. That's the cool thing. We can now do it algebraically because what we have here is an exponential equation. And I'm going to solve this equation for t. And just like I would solve any equation, I want to get 2 to the t all by itself. So I'm going to divide both sides by 1,000. This is going to seem easy after the one we just did. I divide both sides by 1,000. The left side reduces to 50, and I have 2 to the t. So to solve this, I take the natural log of both sides. Natural log of 50 equals, and I'm just going to skip that step, call it t times natural log of 2. Do you see what I did? What I did is natural log of 2 to the t comes down in front. Okay, I just used my log property right away. Now, t's just got a number multiplying it. The number's a natural log of 2. So to undo multiplying by the natural log of 2, I divide both sides by the natural log of 2, and there's my answer. So how many years is it going to take for the rabbit population to get to 50,000 from 1,000? You'd say, wow, that's quite a lot of growth, but let's see how many years it's going to take. Natural log of 50 divided by natural log of 2, 5.6 years approximately. So squigglies, 5.6. So approximately 5.6 years. Not very long to get up to 50,000, those little rabbits. All right. So now you can answer any kind of how long question. If you want to know, like Amy told me she has $10,000 she doesn't know what to do with. So I told her about an investment that gets 5.5%. She's going to invest it. She wants to know how long it's going to take to double. So you can answer questions like that now. Let's see how we would do that one. Yeah. So if we use a continuous, if we use our PERT, PE to the RT, and she's got $10,000 to invest, and she's found this great investment at 5.5% per year, and we want to know how long to double. This is a little sidetrack. I love these. I like it now when you know natural logs, so I can show you these are logs base 10 even. There's a rule of thumb. Anytime you want to know how long it's going to take something to double. So for example, right now, private school tuitions are raising at the rate of about 6% a year. So Hampshire College, about $62,000 a year to go to Hampshire College. We could now figure out how long it's going to take for that tuition to double at the rate of 6% a year. Anytime you want to know how long it's going to take something to double, as long as you have the rate, you can use this estimated, this rule of thumb. Here's the rule of thumb. It's called the rule of 70. You take 70 and you divide it by your rate and you get the time to double. So 70 divided by 5.5%. This is just a quick way to do it, okay? So 70 divided by 5.5%, 70 divided by, 5.5. This is about a little more than 12 years, closer to 13, right? About 12.7. So about 12.7 years. That's our rule of thumb. So the question is, why do we use a 70 there? And in a second, I'm going to show you why that 70 is used. Well, first of all, 70 is a nice number to divide into. All right. No, you just use the rate. You don't use you just use the 5.5. Yeah. No, in our calculations that we do in class, you have to change it to decimal. Okay, because really what this is, Gina, is this. But they just multiply everything by 100. Okay, so suppose we want to take that 10,000. We have e to the point. Now we do the 5t. And over here, we want to know when it doubles. So what's going to be the value I put right there? 20,000, right. I want to know when it doubles. So look, anytime you ask a doubling question, the number you get on the left-hand side is always going to be a 2 there, always, because you're asking when will it double. If I asked you when would it triple, what would be here? A 3. Now look, I take the natural log of both sides. I get 0.055t times the natural log of e, which is just 1. I divide both sides by 0.055, which is t. So Gina's question was appropriate. What is the natural log of 2? What do you guess it's close to? Natural log of 2 is 0.6931, blah, blah. So if you have a 0.69 in there and you multiply top and bottom by 100, you get 69 over 5.5. But they don't want to call it the rule of 69, so they call it the rule of 70. All right? Now my teenager would be laughing away. All right. So natural log of 2 divided by 0.055. So this will tell you exactly 12.6 years. Look at how close that estimate is. Okay. So I did a little divergent thing here. Sorry. I just like it when we get to this point because you can ask these questions. So how long is it going to take, roughly, how long is it going to take the tuition at Hampshire College to double? 70 divided by 6. About 11 and a half, 12 years. So if you're thinking about having a kid, well, if you already have a kid, I guess you already have to have it if the kid's going to go to Hampshire College at 18 or so. 12 years, right? My daughter's just decided to go to Warren Wilson. It's 40,000. Right? She was going to go to Oberlin 2 years ago. That was 60,000. So it's nice. She also got accepted. The only reason I know about Hampshire, they're trying to coax her to going, and it was 62,000+ a year. Of course, they gave her a scholarship for 16,000, but still, you're looking at $46,000. So it's crazy. It's just nuts. Yeah. Yeah, right. Right, doesn't put a dent in it. All right, I'm going to skip this for now. If you see a mixed equation, I'll just tell you a hint. If you want to do this, you factor out your x's, and you have e to the x, you divide. I mean, you can look in your book on that. I want to get to log equations for you. So now can you see the bold? Yes. Okay. If you have a log equation, your strategy is always what it is whenever you solve an equation. You want to isolate your logarithm, a single logarithm. Single logarithm. So guess what? You're going to have to use some of your log properties to squish them back together, to condense them. All right? Your first one, what would be a fantasy equation that would look like that first equation? What might a fantasy equation look like? A real simple fantasy equation for the first one. 2x equals 4, right? If I gave you an equation like that, you want to isolate x and solve. To isolate x, you would do what to both sides? Divide by 2. You're going to do the same thing here. Divide by 2 on both sides. So here's our fantasy equation. Okay. When I divide by 2 on both sides, I'm left with log 5x equals 2. Now, guess what, folks? Log equations are easier. Yeah, right, Linda. They're easier to solve. Why are they easier to solve? Because I can take this log equation and I can write its equivalent exponential form, right? What's the base on that log 5x? What's the base? It's not there, but you know what it is. Not 1. When I just write log, 10. That's our common log. So this is really log base 10 of 5x equals 2. I'm just going to throw that in for you so you can see it. I'm just going to put it in kind of like that. So this is log base 10 of 5x equals 2. I want to turn this log equation into exponential. What's the base of my log? 10. So that has to be the base of my exponential. What's my log equal to? 2, which is a power or an exponent. So this says 10 squared is 5x. Hey, I can solve that equation, no problem. 100 equals 5x. So x has got to be 20. Can it really be that easy? The answer is yes. It really is. As long as you know how to turn a log equation into an exponential and go back and forth, no problem. You can check that on your own. All right. Now, let's do a fantasy equation for the next one. The next one says log 4x, log base 2 of 4x equals 2 minus log base 2 of x. So a fantasy equation for this might look like this. 4x equals 2 minus x. There's my fantasy equation. See, all I did was take out the log base 2 in front, right, to make my fantasy equation. So if you had a fantasy equation like that, Brittany, what would you do to solve that equation? Forget about all this log stuff. Here it is. 4x equals 2 take away x. How would you solve that? You add x to both sides, right? Remember, we're trying to get our log base 2 on one side of the equation and squish it together to make a single log. Just like when we have x's on both sides of the equation, we want to get all our x terms to one side of the equation, right? And then we condense it into a single number times x. So it's no different, folks. You add log base 2 of x to both sides. Log base 2 of x, right? So what do I have on the left side? Log base 2 of 4x plus log base 2 of x equals 2. My fantasy equation would have looked like 4x plus x equals 2. That's what my fantasy equation would have looked like. Now, in my fantasy equation, I add 4x and 1x to get my single term. How do I put these two logs that I'm adding together? When do I add my logs? When do I add my exponents? The bases are equivalent. So what do I do to make this into a single log, log base 2? How do I make it into a single log? what do I do to the 4x and the x? And how do I combine them? Nope. Multiply. When I multiply exponential expressions with the same base, I add exponents. That's what you recall. Here you're adding exponents. So your original numbers were being multiplied, your 4x and x. So this looks like this. 4x times x equals 2. How can I simplify 4x times x? What can I call that? 4x squared. Okay. 4x squared. Okay, so there's my log equation. I want to make it into an equivalent exponential equation. What's my base of my log? What?
4x squared, doesn't that equal 2x squared? So it would be 2 times 1 plus 2x.
Yeah. I think I'm gonna do it a little easier, okay? But we can look at yours in a minute, okay? But everybody with me so far? 4x times x is 4x squared. So how can I turn this into an exponential equation? What would the exponential equation look like? Cooper? 2 is my space. My answer to a log is the exponent, and the number I'm taking the log of is my solution on the other side, my right-hand side in this case. Okay, not my solution, because the solution is the value for x. Okay, so can I solve this? I hope so. 4 equals 4x squared. This is just a baby quadratic equation. So 1 equals x squared. So x squared equals plus or minus 1. Hey, I'm done, right? Nope. Check your answers. Remind me again, we were taking log base 2 of x was our log. What is the domain for my log base 2 function, which looks like this? What's my domain? It can't be negative or 0, right? So you got to make sure that when you plug your, oops, this should be an x here, not a, when you plug your answer back in, you don't get negative. So let's try 1. If I go back to my original equation, I get log base 2 of 4. No problem there. Equals 2, take away log base 2 of 4. That's okay. The left side equals the right side. So I can say x equals 1. But now I check x equals negative 1. The minute I put it in here, what kind of number do I get? 4 times negative. No go. So you have an extraneous solution here. Your extraneous solution is your negative 1. So you only have one answer here. So you always got to check because of the idea that you may introduce an extraneous solution. All right. So this one, you already have your logs on both sides of your equation. The bases are the same. What's the base here, Ben, on this left side? What's the base, even though you can't see it? 10. So let's put them together through multiplication. So this is log of x times x minus 3 is equal to 1. X times x minus 3 is x squared minus 3x equals 1. Now I turn that into a log base 10 problem. See you Friday, Austin. Log base 10. So this is log base 10 of x squared plus minus 3x equals 1. So I turn it into an exponential, I think, right? So my base is 10. My exponent is 1. And that equals x squared minus 3x. So 10 equals x squared minus 3x. What type of equation is that? Quadratic. How do I solve a quadratic? Set it equal to 0 and factor if you can. That's the easiest way to do it. So what are the factors of 10 that differ by 3? What are the factors of 10 that differ by 3? 2 and 5, or 5 and 2. The 5's got to carry all the negative weight. The 2 carries the positive. So x equals 5, x equals negative 2. But if I go back and look at my original equation, I can't have a negative 2 in for x. So my answer is x equals 5. So try the next problem on your own. I don't really want to do that to you. All right. All right, so this is the final thing you need to do for today. If you're told that log of m, log base 10 of m, is equal to log base 10 of n, then you know m is equal to n. This is just like when we relate the bases. If I say b to the m equals b to the n, you know m has to equal n. It's the same idea. So what you want to do here is you want to get a single log on each side. Well, your left side already has a single log. So you need to combine these so you have a single log. So this uses your other property, one of your other log properties. When we subtract exponents, we were originally dividing the 7x minus 23 by the x plus 1. So we put the single natural log in front always, and we say 7x minus 23 over x plus 1. All right. So this looks like log of m. We got the same basis here. Whenever you see an equation like this, you can simply remove the natural log, because to make these equal, you have to make x minus 3 equal to this expression, 7x minus 23 over x plus 1. So this simply becomes x minus 3 equals 7x minus 23 over x plus 1. So we are back to like the second, literally our second class, where we had a rational equation. And to solve this equation, you have two approaches. Multiply both sides by the LCM. There's only one denominator here, so you multiply both sides by x plus 1. Or hopefully, by now, you recognize that's a proportion, and you use your cross products, which gives you exactly the same answer as you would have gotten if you multiplied both sides of that equation by x plus 1. So you get x minus 3 times x plus 1 equals 7x minus 23. What I have on the left side is going to turn into a second degree trinomial. So therefore, I know I end up with a quadratic equation. So I solve my quadratic equation for 0. And luckily, I can factor again. Factors of 20 that add up to 9 are 5 and 4. They both have to carry the same sign. X equals x minus 5, x minus 4. So x is 5 or 4. Check it back in your original equation and make sure when you substitute 5 or 4 in for x, you don't get a negative number. So let's see. 5 minus 3 is 2. Okay there. 35 minus 23, positive. 5 plus 1, positive. So 5's okay. That's okay. Let's try 4. 4 minus 3 is 1. Okay. 28 minus 23 is 5. Okay. 4 plus 1. Okay. So this has two answers. Okie doke. See you on Friday. Don't forget, get here early. Bring your notes, your cheat sheet.